Bom dia a todos. Só para avisar que daqui a pouco a gente já está começando, tá bom? Só para aguardar um pouquinho.
morning, Andre. How are you?
Not too bad. Not too bad. Not too bad. Enjoying the afternoon here. Yeah. Good morning, Michael.
As far as I can see, your webcam is fine. Your microphone is fine. Thanks for checking.
Thank you.
Bom dia, bom dia, bom dia a todos. Sejam bem-vindos ao nosso 15º Wesaac, o segundo seguido da pandemia online. Mais uma vez, a gente não pode estar junto presencialmente, mas a gente está aqui fazendo o máximo e tudo que é possível para que a gente possa ter esse momento dentro da nossa comunidade de agentes aqui dentro do Brasil. Então, dada essa longa espera desde o nosso último, de coração grande, venho desejar um bom dia a todo mundo, dizer que o evento foi preparado com grande carinho pela organização, por mim, pelo Michael, sempre com apoio do nosso comitê consultivo, com quem eu deixo aqui a grande contribuição que eles dão sempre para a gente, sempre nos orientando. O evento está com grandes palestras, com grandes temas muito interessantes, temas muito bem voltados assim, para a atualidade do que a gente tem trabalhado no mundo. A gente trouxe 2 pessoas de fora. Hoje a gente vai ter a palestra do Andrei, que vai ser com certeza incrível. Teremos a nossa primeira sessão técnica também, um mini curso do Jomi, que a gente está muito ansioso também para aprender sobre as novidades que a gente tem dentro do Jacam hoje em dia, né? O que ele tem preparado para a gente aqui. Vale ressaltar que a gente está ao vivo no YouTube, então podem dar oi, que as pessoas estão ouvindo vocês por lá. O RNP vai ser a nossa plataforma na qual a gente vai se comunicar, com quem a gente vai se falar aqui, vai passar todas as informações, palestras e tudo mais. E o Slack vai estar lá disponível para a gente fazer algumas discussões, algumas perguntas que vocês tenham para fazer aos nossos palestrantes ou pelas discussões das sessões técnicas. Tá bom? Com isso, eu abro a minha palavra aqui também para o Maicon e para o Michael, para que eles deem boas-vindas a vocês também, e que todos nós tenhamos um excelente dia e um excelente evento, e espero que todos estejam bem e muito longe do Mocoronga, até o momento que a gente possa estar junto de novo. Tá bom? Maicon, palavra com vocês.
Bom, de minha parte, bom dia a todos, e faço coro ao que o Pantoja aí já falou, né? Damos as boas-vindas, preparamos tudo com muito carinho, esperando que a conferência seja de proveito grande para todos. Agradeço a participação de todos os inscritos, também daqueles que vão nos ajudar e nos trazer informações e novidades com palestras, com as oficinas, também o nosso comitê consultivo, que foi de grande ajuda. Enfim, aqui estamos para mais essa conferência, num modo excepcionalmente virtual novamente, e espero que todos aproveitemos.
Bom dia, pessoal. Espero também que todos estejam bem. Agradeço a presença aí de todos os participantes, os palestrantes, o comitê consultivo, enfim, todo mundo que está participando de todo esse evento, né? Em especial também o Pantoja, o Michael, que a gente formou um time aí para organizar esse evento, e toda a equipe ali dos alunos do Pantoja também que estão por trás aí nos bastidores, sempre dando um grande apoio, né? A gente tem que lembrar deles aí também, né? Então, aproveito para desejar a todos aí um ótimo evento. Vocês não estão me ouvindo? Então? Ok. Kleber, talvez o teu áudio. Ok, então, só desejo então a todos um ótimo evento, e a gente então passa a palavra aí para o Mike. O Mike então vai apresentar o Andrei, e a gente já inicia com a nossa primeira palestra do dia.
Só uma instrução. Muitas vezes, quando a gente está na RNP e a gente não consegue ouvir ou não consegue falar, se não tiver desativado ou tiver tudo certo com a manipulação da ferramenta, sai e entra de novo, que talvez possa ser no momento da entrada alguma coisa que dá algum bug, alguma coisa assim. Então, só tenta sair e entrar de novo, tá bom? Michael?
Ok, obrigado, pessoal. Então, a gente vai começar com a nossa primeira palestra do evento, né? Cujo título é Hypermedia Multi-Agent Systems, Rethinking Multi-Agent Systems for the World Wide Web, com o Andrei Ciortea. Eu vou apresentar o Andrei primeiro em português e depois a gente apresenta ele novamente em inglês, introduz a palestra e, enfim, aí o Andrei nos começa, né? Bom, o Andrei Ciortea, ele é pesquisador em nível de pós-doutorado no tópico de sistemas baseados em interação e comunicação na Universidade de St. Gallen, na Suíça. É também colaborador externo na Universidade de Côte d'Azur, na França. Os principais interesses do Andrei em pesquisa incluem sistemas multiagente baseados na web, sistemas hipermídia, web das coisas e redes sociotécnicas. O Andrei recebeu o prêmio de melhor artigo na 6ª Conferência Internacional de Internet das Coisas em 2016. E antes de ingressar na Universidade de St. Gallen, o Andrei teve um tempo como pesquisador visitante na Siemens durante 6 meses, nos Estados Unidos, onde ele foi o principal pesquisador e arquiteto líder de um sistema para manufatura inteligente que integrou sistemas multiagente com o web das coisas. O Andrei também co-organizou o seminário Dactyl em Agentes Autônomos na Web, em fevereiro desse ano, o primeiro workshop em sistemas multiagente hipermídia, que foi realizado junto com a Web Conference em 2019. Ele é membro fundador da Associação Romena para a Inteligência Artificial. O Andrei obteve seu doutorado em 2016 na École de Mines de Saint-Étienne, em supervisão conjunta com a Universidade Politécnica de Bucareste. A gente, então, agora passa a apresentar o Andrei também em inglês e a palestra também vai prosseguir em inglês. Okay, our first lecture has the title Hypermedia Multi-Agent Systems, Rethinking Multi-Agent Systems for the World Wide Web. It will be given by Andrei Ciortea. Andrei Ciortea is a postdoctoral researcher with the chair for interaction and communication-based systems at the University of St. Gallen, Switzerland, and is an external collaborator of the Université Côte d'Azur, France. His main research interests include web-based multi-agent systems, hypermedia systems, web of things, and social technical networks. Andrei received the Best Paper Award at the 6th International Conference on Internet of Things in 2016. Before joining the University of St. Gallen, Andrei had a 6-month research visit with Siemens Corporate Technology in Berkeley, USA, where he was the principal investigator and lead architect of a system for intelligent manufacturing that integrated multi-agent systems with Web of Things systems. Andrei co-organized the Dactyl seminar on autonomous agents on the web in February of this year. The first workshop on hypermedia multi-agent systems co-located with the web conference in 2019, and he is a founding member of the Romanian Association for Artificial Intelligence. Andrei obtained his PhD in 2016 from Mines Saint-Étienne and the University Polytechnica of Bucharest in a joint supervision. So, Andrei, thanks very much for accepting our invitation. Welcome to Wesaac, and feel free to move on your talk.
Good morning, everyone. Thank you very much for the very kind introduction, and thank you for the invitation. I'm very glad to be here. I will share my screen in a second. Okay, could you please confirm that you can see my slides?
Yeah.
Okay, perfect. So thank you again for the invitation. I'm very glad to be here. And I am quite excited about the topic of today's lecture, which is really at the heart of my research. And I hope I will manage to give you some of my enthusiasm for this topic. So just to let you know, I do not see the video feed, and I also do not see the chat window. So please do not hesitate to interrupt me if you have any questions, okay? So to begin from my research, really, during my PhD thesis, I started from the multi-agent systems community, and I was looking at applying multi-agent systems to the Internet of Things. And then in that process, I got to learn about the Web of Things and how the web works and to better understand the design of the web architecture. And then since defending my thesis, I've been mostly working on trying to transfer some of those lessons back to the engineering of multi-agent systems. So now, the first question that would come to mind is, why would that be interesting in the first place, right? So why study the web architecture? And I think that the web is really a one-of-a-kind system. So it is a distributed hypermedia system that managed to scale up to the size of the internet. And it was able to do that because of architectural properties that were designed into the web architecture. So in the words of Roy Fielding, who defined the architectural style of the web is constantly running, always changing, anarchically accessed, and independently deployed. And I am going to unpack some of those properties in the first part of the lecture. Then another statement that I like very much comes from Tim Berners-Lee, so the one who invented the web. And he makes a point that the web was designed not so much as a technical toy, but rather to help people to work together. So the web was also very successful as an internet scale system of people. And I think we've seen this especially during the pandemic times, right? So we achieve most of our everyday goals by using this internet scale hypermedia environments. We do our online shopping, we plan our travels, we interact, we do pretty much everything through the web. So in a sense, we already have a worldwide system of billions of human agents that can interact through the web. And we know that the web can accommodate billions of agents. But really to stress the success of the web, it's important also to contextualize a bit. So the web is the most successful system, hypermedia system that we know of, but it was by far not the first hypermedia system. So the proposal for the web came out in 1989, but the term hypertext was actually coined by Ted Nelson in 1965. And you can find this paper online. And perhaps another face that is more familiar is Alan Newell. So Turing Award winner, Alan Newell is known for many different contributions to computer science, or the SOAR cognitive architecture, contributions to list processing, and so on. And he was also one of the main people who coined the term human-computer interaction. And in the early 70s, Alan Newell was actually involved in the development of a hypertext system called Zog. This is a system that was deployed on the USS Carl Vinson. This is one of the 10 nuclear-powered super carriers of the US Navy. There was also a commercial version released and so on. There is really quite a bit of interesting history around Zog. If you want to learn more, there is a talk by Alan Newell on YouTube where he also mentions Zog, and there are a couple of papers that describe the system in more detail. So again, going back to the web was not the first hypermedia system. There were already several systems available. There was an entire research community, but the web was doing a few things very differently. And in fact, there is a story that is quite famous in the web community, which is about Tim Berners-Lee submitting a paper in 1991 to the Hypertext Conference. And that paper was rejected for oral presentation. It was only accepted as a poster contribution. And the image that you see here is the actual poster that was presented by Tim Berners-Lee at the Hypertext Conference. And one of the reasons for which it was rejected were broken links. So that 404 status code that we find so often on the web. And for the hypertext community at the time, it was really not conceivable to have broken links. It was too trivial. But Tim Berners-Lee replied to that is that individual links are allowed to break, so the entire web does not. So it's really all about design trade-offs. And this will bridge into the first part of the lecture, which is about REST, the architectural style of the web, which captures the design rationale behind the web architecture. And in particular, I will try to give you a concise, intuitive view on how REST helped the web scale up to the size of the internet. And a big part of that answer is the uniform interface constraint. And we're going to talk quite a bit about uniform interfaces today, and it will be a central tack of the lecture. And then I'm also going to mention briefly some recent developments around the Web of Things, which we believe can unlock many new practical use cases for multi-agent systems on the web. So this will be the first part of the lecture. This will be more of a lecture. Then the second part will be closer to a research talk, I would say. So in the second part, I will start with a web perspective on web-based multi-agent systems. And then I will present some of the work done together with some of my collaborators around this topic. And in this part, I also prepared a couple of live demonstrator and a demo video, so I hope this will be exciting, and I'm hoping that this will also open up the floor for discussions. So, okay, so just to mention once again, so I do not see the chat window and I do not see the live video feed, so please do not hesitate to interrupt me if you have any questions. Okay, so to begin with an intuitive analogy for REST. So what we have here is a really nice picture of Reims Cathedral in France. And as soon as we look at this picture, we are going to notice a number of features. So we see those pointy arches, those rib-vault cages, and so on. And as soon as we look at this image, we can immediately tell that this building was designed in the Gothic architectural style because of those features. In a rather similar way, REST is the architectural style of the web. And REST was also designed to emphasize specific features, in particular to emphasize internet scale distributed hypermedia interaction. So this is what REST was designed for. And then when we take REST, which is essentially a set of architectural constraints, and we apply it to an architecture for a distributed hypermedia system, what we get is something like this. So this would be a snapshot or an illustration of the web architecture. And in REST, we have three types of architectural elements: components, data, connectors. And now I'm just going to give a very brief overview of how all these elements interact with one another. So components communicate through request-response interactions. Then they use either a client connector, a server connector, or both. We have on the left-hand side, we have origin clients. In the web community, these are typically called user agents, but I'm using the term origin client to avoid that name clash. And these are essentially components that use a client connector to issue a request. Then on the right side, we have origin servers. These are components that use a server connector to issue responses, and in between we have intermediaries. These are components that use both a client connector and a server connector, but in a very specific way, to forward requests and to forward responses. Then components exchange representations of resources, where a resource is really the key abstraction of information on the web, so anything that can be named is a resource. A representation is data that encodes information about either the current or intended state of a resource. And then components can also negotiate different representation formats that are being used in the exchanges. So I'm sure this is all quite familiar. This is how the web works. These are the three main types of web components. And all this interaction rationale comes from the REST architectural style and the 6 architectural constraints that were defined by Roy Fielding in his PhD dissertation. So unfortunately, we don't have time to discuss each of them. What's important to note here is that REST is a coordinated set of architectural constraints. What this means is that all the constraints are applied as a whole. We cannot cherry pick the constraints. And there is also a lot of interesting interaction among the different constraints. And this will come up a bit later on when we talk about internet scalability. And each of these constraints implies a design trade-off. So for instance, the cache constraint, that one is quite easy to see. So our browsers have a cache, so we can cache information on the client side, on an origin client. We can also have shared caches on an intermediary. That is a common deployment pattern at the boundary of an organization. And there, the benefit is quite clear. So as soon as we cache data, we eliminate network interactions. So we improve the user perceived latency. But then the downside is that cache data can also lead to stale data. So we have to be very careful on how we use our cache settings. So each of these constraints imply various design trade-offs, which are quite interesting. But what we are going to discuss about today is really the uniform interface constraint, which is really central to REST and what distinguished REST from other architectural styles. And the uniform interface actually comes from 2 very simple ideas that really shaped the web. And here by simple, I don't mean trivial. Simple rather in the sense of elegant. The first idea comes actually from the initial proposal for the web, which was written in 1989 by Tim Berners-Lee. And this is an image from that proposal. And essentially the web was proposed as an information management system at CERN. So the problem that they had at CERN was that they had scientists visiting from all over the world, and then as soon as they got to CERN, they had to interact with many different systems, which were quite heterogeneous. Then they would be doing some work there for a number of months, then they would go home, they would have to access those systems remotely as well, and apparently this was a bit of a problem. So the web was actually proposed initially as a sort of application integration architecture, and you can see this keyword here, unifies, in the initial diagram of the web. And this was really one of the distinguishing features of the web compared to early hypertext systems. And this is a point that Tim Berners-Lee makes in that paper, that early hypertext systems would justify their usefulness solely on new data, whereas the web was actually to be integrated with existing systems. And I pulled out a quote that I find very interesting from that paper, in which Tim Berners-Lee points out that if there is an existing base of data personnel, for instance, then to which new data could be linked, then the value of each new piece of data would be greater. So I really like this quote because you can see already kind of like the term linked data in there. So this is an idea that was already there in the early days of the web, just like the semantic web and so on. But really the core idea here, so the core simple idea that really shaped the web was to integrate existing systems behind a simple uniform hypertext interface that all users can access from anywhere in the world. This was one of the very simple ideas that really shaped the web and the web architecture. Then the second idea around uniform interfaces comes from Roy Fielding. And there is a very nice keynote from 2017 that you can find online. I have added the link here in the footnote, a keynote from Roy Fielding, where he makes a point about his previous experience with Unix pipelines. So he was doing a lot of sysadmin work, and you've probably worked with Unix pipelines before. And you know, you have this uniform interface that allows you to pipe the output of one process to the input of another process. And this is great because it is very flexible and it allows us to build very complex pipelines. So for instance, this would be just an example of a brain teaser that I did one evening. It probably took me a bit more time than I'm willing to admit, but it shows the sort of complexity that we can achieve with the Unix pipeline. And Unix pipeline follow an architectural style that is known in the software architecture literature as pipe and filter. So this idea of piping a component into another, and then we can also do some processing of the output of the previous component. So what is the core simple idea here? Well, to make an intuitive analogy, Legos applied to software, right? So simple uniform interfaces enable reusability, recomposability of components in many innovative ways. So we know that from Unix pipelines, but just think about this analogy with pieces of Lego. So just the amount of value that we can get from a set of Lego pieces. So now imagine that we could apply the same principle to the web architecture. And this is what Roy Fielding went for. So now going back to a diagram that we saw earlier, the uniform interface is central to REST because it allows us to insert intermediaries all along the request response path. So again, if we think about pipelines, you can see from left to right a sort of a pipeline, which is about requests being propagated. And then from right to left, we have another pipeline, which is about responses being propagated from origin servers to origin clients. And we can use intermediaries for many different purposes. So we can use them for caching. We already mentioned that. For bridging, here in the bottom of the diagram, you see that actually I have here a gateway, which talks to a non-web origin server. So this would be a Bluetooth device. This is a common deployment pattern in lighting systems. So if you buy any of the systems like Philips Hue and so on, usually you have a set of light bulbs that talk to a bridge using Zigbee Light Link, and then the bridge will expose an HTTP endpoint that we can actually use for development. So we can use intermediaries for bridging. Another very important usage would be load balancing. So in the top of the diagram, I have here a reverse proxy, which essentially abstracts away whatever happens behind it, so information hiding, and then I can bring up new origin servers at runtime and balance the load across the different origin servers. So I'm hoping that this image and this discussion kind of like gives this view of pipelines applied to the web architecture. And why is this important? Because then components can be developed and they can be deployed independently, and they can also evolve independently over long periods of time. Just like our processes that we can use in Unix pipelines can do the same. And this is really one of the very core features that allowed the web to scale up to the size of the internet. And intermediaries have really proven to be essential for building an internet scale system. But now the question would be, okay, so what is the trade-off here? So there is no free lunch, and we mentioned that each of these constraints implies a trade-off. So clearly on the upside, it will increase the evolvability, reusability, simplicity of the system, but then what is it that we have to pay? Well, we have to pay efficiency. So using a general uniform interface might be inefficient as compared to using an interface that is specific to a given implementation. So to make an analogy here, just imagine a group of people from different nations interacting with one another. So pretty much what we are doing right now. So to be able to interoperate, we have to use a shared language, in this case, English. But for me, I'm originally from Romania, so English might not be the most efficient way to communicate my ideas, right? Because it might not be as expressive as I want it to be. And also it might take me some effort to translate ideas from my internal representation to this interface language that I'm using, which is English. So the same trade-off applies to web components. So the uniform interface is great for evolvability, it decouples the web architecture, but it also degrades efficiency. And of course, before moving forward, as I was saying, all the constraints in REST interact with one another. So it's not just the uniform interface, but we get intermediaries also because we have this sort of client-server separation of concerns. We have stateless interactions. So this allows me to insert intermediaries all along the request response paths and so on. So really, all the REST constraints interact with one another to give us this design rationale that allow the web to scale up to the size of the internet. So to continue with an intuitive understanding of the uniform interface constraint, really the core idea here is to hide away the implementation details of components behind a uniform interface that is based on standardized knowledge. And I'm going actually to continue with the shared language analogy. So the idea is that the uniform interface constraint prescribes there ought to be a shared uniform language composed of verbs and nouns. Okay. More precisely, a small set of verbs with well-defined semantics that are agreeable among origin clients, origin servers, and any intermediaries in between. So this is a very important point. The semantics have to be agreeable because otherwise components would not be able to talk to one another in a reliable way. Then for HTTP, we have the get, post, put, delete, patch, and so on verbs. CoAP, the Constraint Application Protocol. This is the web protocol for constrained devices for the Web of Things. And CoAP defines a similar set of verbs. And the semantics of these verbs are defined by the IETF in the RFCs that define these protocols. So that is where the semantics are defined, and then we hard-code those semantics into the components. And then on the web, we also have a large set of nouns with well-defined semantics that are also ideally agreeable among origin clients, origin servers, and any intermediaries in between. So again, semantics. So semantics are very important in the web architecture, and in my mind, I cannot imagine hypermedia without semantics. In a REST system, the nouns are resources. So this is the key abstraction of information. Resources have representations, and the semantics of the representations are defined by media types, where a media type is just a two-part identifier for a given representation format. So text HTML is the most common one. Application JSON, this is another common media type that is being used, especially for web APIs. And there is really a long list of media types. So media types are registered with IANA. So this is the same association that manages internet addresses. And as you can probably see now on my browser, anyone can register a media type. So if you wish to register a media type with IANA, you are welcome to do so. And as you can see, there is actually a huge list of media types. So we don't usually use all these media types, but the media types are there. Now, why is this important? Well, let's go back to the example of a lighting system, right? So something like Philips Hue or LG or whatever. So they all follow a rather similar deployment pattern where you have light bulbs that talk to a gateway using ZigBee Lightning, and then the gateway exposes a web API. So then my origin client, oops. Okay, now you should see my screen. So my origin client can then change the state of the light bulb by sending an HTTP put request with a payload, which is usually using JSON as a representation format. The payload could be something like on true. But here we have a small inconsistency. So the thing is that JSON specifies the syntax of the representation, but it will say nothing about the actual semantics. So what does on really means here? Who specifies that? Well, if I'm just using application JSON, I would need to find that information in some documentation, and then I need to hardcode it into my origin client. And this is how things typically works. And that is a problem because it leads to tight coupling. So going back to the analogy with the pieces of Legos, perhaps you've played with Lego at some point, and one of the pieces had a small dent into the uniform interface. And that is quite annoying because just a small dent will destroy the standard interface, and then the piece will not fit with all the other pieces, right? So it is the same here. It might appear trivial, but it is not. If we don't have a way to capture the semantics through hypermedia, so as in-band information, then we need to hardcode the semantics into the components, which is a bit of a problem. So what could be the solutions here? Well, one solution would be to define a subtype. It can be a JSON-based format that captures those semantics. And if you go back to the YANA webpage, you will see that, in fact, there are quite a number of JSON-based subtypes. So for instance, this one, activity plus JSON, this was defined by the W3C for activity streams. Then later in the lecture, we are going to talk about a JSON-based format for the thing description defined for the W3C Web of Things. So here we also have a media type TD plus JSON, which is a JSON-based media type that also captures the semantics of the representations within a given specification. So this would be one solution. We define a new media type. The problem there is that then everyone has to implement that media type, or we can use semantic models. So we can use a standard RDF serialization format, and then we can just move the interoperability problem one layer above. And there we talk about ontology alignment and so on and so forth. So this is an intuitive understanding about the uniform interface constraints, so a shared language composed of verbs and nouns. What's important here are the semantics. So in my mind, I cannot think about hypermedia without semantics. So although when we mention semantics in the context of the web, we mostly think about the semantic web, semantics can also be conveyed in other ways on the web. But this intuitive definition, of course, is not complete. So a more precise definition is given in Roy Fielding's thesis, where he defines the uniform interface constraint as a set of 4 interface subconstraints. And I'm sure that most of you are familiar with these constraints, so I will go a bit faster through these constraints. So the first one is uniform identification of resources. So resources must have uniform identifiers with global scope, such that they can be referenced independent of context. And on the web, we use URIs. The second constraint, manipulation of resources via representations. And this is a big one. So the idea here is that clients don't have direct access to resources. They only send and receive representations of resources to and from servers. And this constraint is so important that we can actually find it in the name of the architectural style, so representational state transfer. This is what allows that decoupling between an internal data format and the representation format that is being exposed through the interface. Then we have self-descriptive messages, so HTTP requests, co-op responses, they all include headers, which give us metadata that describes the meaning of the message. So this is where we get the standard verbs, and this is also where we get the standard media types, among many other things. And then the last one, which is a very important one for the lecture today, is hypermedia as the engine of application state. And this is one of the constraints that are many times overlooked. And I'm going to unpack that in a bit. But before I do that, I just wanted to draw an analogy here with the rules of linked data. So perhaps you've seen the rules of linked data before. These were published in 2006 by Tim Berners-Lee. And now if you look at the rules of linked data, we can see some sort of analogy here. So the rules are: use URIs as names for things. Use HTTP URIs so that people can look up those names. When someone looks up a URI, provide useful information using the standards, for instance, RDF and so on. And then include links to other URIs so that they can discover more things. This is related to Hypomedia as the engine of application state. So one way to look at linked data and the rules of linked data is that they create a uniform interface for the web of data. And this came up because in the semantic web community, there was a lot of focus on knowledge representation on the web, or knowledge representation in general, but the web part was not so prevalent there. So many data sets were not even available through the web. So this is why in 2006, Tim Berners-Lee started this linked data movement to really bring data on the web under a uniform interface. So again, this idea of uniform interface, it's a simple idea, but it's a very powerful idea that really shaped the web as we know it today, and a very big difference from other systems. So before I move on, I will stop and ask you if there are any questions so far. And I will also check quickly the chat window. Okay, so I will then move on. So now we get to one of the constraints that are really at the heart of the web architecture, hypermedia as the engine of application state. And so far, I've talked a lot about hypertext and hypermedia, but I haven't really defined what it is. And there are many definitions out there. So the first one goes back to 1965, but the definition that I liked the most was given by Roy Fielding in 2008. And Roy Fielding defines hypertext or hypermedia as the simultaneous presentation of information and controls such that the information becomes the affordance through which the user obtains choices and selects actions. I very much like this information because this link here to affordance theory. So affordance here comes from affordance theory. So Gibson's affordance theory from ecological psychology, which was brought to human-computer interaction by Don Norman. So affordances are also very important on the web. Now, to give you an intuitive definition for affordances, it's interesting to think about what are affordances in the physical world. So for instance, if you look at this image, do you notice something peculiar? And this is an actual question, so this is not a rhetorical question. So if you look at this image, do you notice something peculiar? Any brave soul that would like to take a try at answering? So, anyone? Do you see anything peculiar if you look at this image of the door? So, to me, when I look at this image, it seems like there is a small contradiction there. Because I see a sign that says push, but then if I look at the door handle, it seems like the door handle would signal to me that I can open this door by pulling, right? So the door handle affords pulling, but the sign on the door says push. So to me, that seems like a contradiction because for pushing, I would rather expect a door handle that looks something like this. So these are affordances in the real world. So these are affordances are interaction queues provided by the environment to the agent, who is situated in the environment. And then we use affordances every day to achieve our goals. So then the question is, how do affordances look like on the web? Well, this would be a hyperlink. This would be just an information of just a piece of text. So just information. This is information with controls. Information that I can actually affords clicking and I can access. Another very nice example that I like comes from Ruben Verborg, a course on web fundamentals you can find online actually. And to really understand the importance of hypermedia on the web, it's interesting to imagine any website without hypermedia. So how would the Google search engine look like? So essentially we would just have the logo, and then if we actually want to perform a search, we would need to have some documentation that would tell us how to use this website. And we could still perform our search by using a query string parameter. But then we need to query encode our search term and so on and so forth. So that would be not very useful. First, we need to have this additional documentation, and then we need to really, let's say, implement that specification. Whereas on the web, we don't have to do that because all this knowledge is provided to the clients through Hypermedia at runtime. So this already sketches a bit the idea of hypermedia-driven interaction. And this is really at the heart of how the web works. So a web application is essentially a distributed finite state machine. So we can have pages that are distributed across many different servers. And then how we typically use the web is that we have an origin client that needs to start from an entry point. So we need to dereference a URI. When we do that, what happens is that what we get back is the current state of the application, the next reachable states, but also Hypermedia controls for transitioning to those states. Then the client has to make a choice. It has to decide what is the next application state. And then this will fire a self-constrained request on a resource for transitioning to that state. So this is a very simplistic mechanism, but it's really at the heart of the web architecture. So hypermedia-driven interaction is really what decouples the web architecture. So URIs, possible transitions to next application state, and also the means to transition to those states are advertised in the hypermedia. They are never hard-coded into clients. This is what allows really components to be developed, to be deployed, and to evolve independently from one another. And an important point here is that without hypermedia, we cannot have a REST style system. And this is a point that Roy Fielding made back in 2008 when he wrote a blog post that to make the point that REST APIs must be hypertext driven. And if you're making a point that hypertext is a constraint in REST, so it's not optional. So let's see what happens without hypertext. And this is how most web APIs look today. So REST-like APIs don't usually use hypertext or hypermedia. So this is just one example of the Twitter API. What happens is that we typically have some API documentation. In this API documentation, we will discover API-specific semantics for the verbs that we are using. So for instance, here to delete a resource, we actually use a post request, and then we tunnel the delete operation through the URI. This is information that now I need to hard-code into my client. Again, Twitter uses application/JSON as a media type. And as we saw previously, JSON is great for capturing the syntax, but it doesn't capture the semantics. And the semantics of representations are actually defined in the API documentation. So again, this is something that we need to hard code into the clients, and this causes tight coupling to the Twitter service. And this is why in the real world, we have to use API versioning. We have to embed the version of the API in a URI or use an HTTP header field such that when we change the API, clients don't break. Because the description of the API is meant for developers. It is out of band information. It is not in the band of communication between the client and the server. So the programmable web so far works quite differently from how the web worked. And this is the point that Roy Fielding was making back in 2008. So now it's interesting to imagine how web services would look like with Hypermedia and with HateOS. So with HateOS, a web API does not need developer documentation, and also it does not need versioning. This would enhance the flexibility and robustness of web-based systems. The idea then is that all links are discovered at runtime, which is much closer to how people navigate web applications. But the challenge, of course, is that then Hypermedia clients also need to adapt at runtime if the links change. And this is really where I think that a new plethora of practical use cases can be found for multi-agent systems on the web. And Hypermedia APIs are particularly useful in the context of the Web of Things, as we are going to see very shortly. But why? Because, well, in the Web of Things, we would expect to have dynamic environments. So we would expect to have devices that appear or disappear at runtime. So then having static APIs that have to be manually programmed into clients doesn't seem like a very viable approach. Before I continue with Hypermedia APIs for the Web of Things, I'm just going to make a small parenthesis around the Web of Things. So what is the Web of Things? And perhaps many of you are already familiar with this evolution. So if you look at the networking stack, the IP protocol is now really a narrow waist for the internet. And then some of the early breakthroughs for the IP-based Internet of Things came in the early 2000s when independent researchers showed that it's possible to bring the Internet protocol to constrained devices. So then we have convergence at the network layer in the Internet of Things. But what happened was that as soon as we went above the network layer, there were different consortiums that were building different stacks of protocols and so on. So we were losing that convergence that we were gaining at the network layer. So then some people started to think about the web as a sort of narrow head for the protocol stack. And this is, in a nutshell, the idea behind the Web of Things. To achieve convergence for the Internet of Things up to the application layer, and this would enhance interoperability, faster innovation, and rapid prototyping. So the first paper to promote these ideas came out in 2007. Now the Web of Things is being standardized through concerted efforts of the IETF and the W3C. And the W3C standards came out last year, so very recently, they were finalized. And we are going to look at two of them that I think are very interesting in the context of multi-agent systems on the web. So the first standard is the W3C Web of Things sync description, which is precisely what we were looking for a bit earlier, a sort of API documentation for machines. It's a machine understandable description of a thing. And this would include general metadata about the thing. So for instance, a thing description of a street lamp would tell us that this is a street lamp. It could also contain links to other things. So for instance, a link to the manufacturer. And then the thing description defines three types of interaction affordances. Properties, which expose the state of a thing. These properties can also be observable. So for instance, that the lamp is on or off. Actions, which we can use to manipulate the state of a thing. So for instance, a toggle action to turn on or off the lamp. But also events. For instance, if the lamp burns out, perhaps it can send a notification to someone. And all these interaction affordances come with hypermedia controls, which convey to clients how to activate an affordance. So for instance, through an HTTP request or a CoAP request. So this is precisely that idea of API documentation for machines that can be discovered in band. And more precisely, this is how a thing description looks like. As we saw earlier, the thing description specification defines a JSON-based format, which is registered with YANA. But it is also compatible with JSON LD 1.1. So we can also treat it as semantic data in the sense of the semantic web. So for instance, here, this representation is compatible with JSON LD 1.1. It has a context element, and here we can define namespaces that point to different ontologies, where an ontology is a formal explicit specification of a conceptualization of a domain. So for instance, in this representation, we see here that we have a light switch, which is defined in the Saref ontology. And then if we go to the Saref ontology, we see that a light switch is a device of a given category, actuator in this case, that accomplishes a specific task, and so on and so forth. So this would be a way to convey more advanced semantics using a thing description. So, okay, this is great. And now, if we look at the Web of Things architecture, which is the second W3C recommendation that came out last year, we are going to see that the Web of Things kind of like follows the same sort of design rationale that we already saw for the web architecture. So we have things, the things carry semantic descriptions, the thing descriptions can be linked to one another and so on. And then we have consumers, which are essentially components that can reliably interpret a thing description and translate it to interactions with a thing. And then ideally, what we want is that a consumer is able to arrive and operate in any W3C Web of Things environment, given a single entry point. So then the question that comes up is, how can we design autonomous consumers that are able to achieve their tasks by navigating the hypermedia and deciding among the various options presented to them? Well, this is where I believe that research on engineering multi-agent systems can really provide many answers, because we already have solutions to design, to program, to debug, to monitor, to regulate, and to coordinate such autonomous consumers. So then the question is the problem solved? Do we need anything else? And we believe we do. By we, I mean me and the wonderful collaborators that you see here. So we submitted a blue sky paper at AMAS in 2019, where we were looking at the last decade of research in multi-agent systems, but also in the web. And we were revisiting one of the questions raised by Jim Handler, so one of the main proponents of the semantic web vision, back in 2007, which was, where are all the intelligent agents? So why don't we already have multi-agent systems on the web? And we believe the answer lies in two sets of arguments. So one is around lack of practical use cases, and this is where the Web of Things can come into play, as well as many recent developments around the web community, which really unlock new practical use cases for multi-agent systems on the web. But we believe that there is still a conceptual bridge that is missing between architectures for multi-agent systems and the web architecture. And I'm going to pick that up back in the second part of the lecture. But before I go on, I just want to stop for a bit and to ask if there are any questions so far. So I see some messages in the chat window. Okay. So please do not hesitate to jump in if you have any questions about REST and the web architecture. So I'm hoping, so I've discussed quite a bit about the web, which might seem a bit weird in the context of a summer school for multi-agent systems, but this is really important to motivate, and I hope I managed to motivate why we think that the web holds some very interesting opportunities for multi-agent systems. So this comes from the recent developments like the Web of Things and so on, and also why the design of the web architecture could be interesting for engineering multi-agent systems. So, okay, then I'm going to move on, and to begin with, there has been, of course, a lot of work on web-based multi-agent systems. So I'm just going to take a very quick web perspective on web-based multi-agent systems. And going back to our blue sky paper, there we really take a far look back, so to the early 2000s, when much of the bulk of the work on web-based multi-agent systems was performed. And in the early 2000s, from a conceptual standpoint, multi-agent systems would typically be composed only of agents. So this was the main abstraction being used at that time to conceive of multi-agent systems, so agents that exchange messages. But then if we look at this conceptual image and we ask the question, what about the web? So what can we do with the web in such a scenario? Well, it would seem like the natural fit for the web is as a transport layer in multi-agent systems. And this is a view that was also enforced by the standards for web services at that time. So the WS star standard, so SOAP, WSDL, and so on, which were using the web as a transport layer. So it's very easy to see that with SOAP, the standard binding was with HTTP, but there was also a standard binding for SMTP. So we could completely throw away the web and insert any transport layer for WS star services. Of course, this was due to some design objectives required at that time. But that is also clearly a problem, because if we can replace the web with any other transport layer, what this means is that the systems we build on top of the web are agnostic to the web architecture. And the same idea was also picked up by FIPA, which provides a specification for using HTTP as a message transport protocol. But really, HTTP is not meant to be a transport protocol. And this is a point that Roy Fielding makes in his PhD thesis. So there is a section which is titled HTTP is not a transport protocol, and there is another section titled HTTP is not RPC. And the key point is that if we use the web only as a transport layer in multi-agent systems, then multi-agent systems remain outside of the web and they are misaligned with the web architecture. So they cannot inherit the properties of the web, which is really what we are going for. But since then, many things also changed in the engineering of multi-agent systems. So now we also conceive of the environment as a first-class abstraction. So there was the workshop series on environment for multi-agent systems. Also the organization, we conceive of the organization as a first-class abstraction. So this image now looks rather something like this. And this is an image of the Giacomo Metamodel, which I think you might be familiar with. And just by looking at this image, it seems like it opens up much more opportunities for integrating with the web. So actually, I started using Giacomo back in 2011. So this is my 10-year anniversary as a Giacomo developer. And this was really one of the core motivations that kept me focused on doing research, because working with Giacomo and seeing the conceptual integration between all these different dimensions, in my mind, opened up a lot of new opportunities for thinking about multi-agent systems on the web. So in this perspective, I'm just going to do a very quick organization of prior work on web-based multi-agent system. And there has been a lot of work using the web as a transport layer. So this would include all the platforms that implement the FIPA, HTTP specification, but also many of the platforms using the WS star web services, which were the main standards for web services back in the early 2000s. Then more recently, now we also have approaches that use the web as an application layer. And we have approaches both without Hypermedia, and more recently, there are several approaches with Hypermedia. So I will not go more into the details, but you have here references for many of these approaches. And the focus of my research is on systems that use Hypermedia. So multi-agent systems that use Hypermedia in their design rationale. And this kind of like sums up to the very ambitious goal that I would see for web-based multi-agent systems going forward. And this is a goal that we set out to do together with collaborators in some of the projects that we are involved in, to define a new class of multi-agent systems that are designed for the web, in the sense that they are aligned with the web architecture to inherit the properties of the web as an internet-scale, open and long-lived system, but are also transparent and accountable to support acceptance by people. And this is really a very ambitious goal. So it is not a research objective for one researcher or a group of researchers, but it really requires a concerted effort of several communities because of all these different research threads that come together. So we talked about web architecture, affordance theory, semantic web, link data, engineering multi-agent systems. So really a lot of different research threads that come together. And this is why a big part of our collective effort over the past few years has also been to try to bootstrap a joint community effort in this direction. So in the introduction, Michael already mentioned the workshop on Hypermedia multi-agent systems organized back in 2019. And then recently in February, we also had a Dutch tool seminar on autonomous agents on the web. So if you are interested in these initiatives, you can also follow this account on Twitter, HyperAgents, or you can visit the HyperAgents website where we are going to post more information about such events in the future. So going back to the research objective, this is really a community effort. But given that this is also very recent work, it would be quite ambitious on my side to try to provide an overview of everything that is happening in this emergent topic. So in what follows, I will focus more on the work done in collaboration with some of my collaborators, so Olivier Bossier, Simon Meyer, Fabien Gandon, Alessandro Ricci, and Antoine Zimmermann. And in what follows in the next 2 slides, I will try to give you an overview of our work so far on hypermedia multi-agent systems from 2013 to present. So these 2 slides should give you the big picture for everything that follows in this presentation. And I'm going to use the Vowels perspective on multi-agent systems. So the 4 conceptual dimensions that we typically use to study multi-agent system: agent, organization, interaction, and environment, just to organize the discussion a bit. So when we started with this work, we started with what we were calling at the time socio-technical networks. So this was part of the work in my PhD thesis. And our objective with socio-technical networks was really to create a hypermedia-based uniform interface for human and artificial agents in the Web of Things. So the focus there was really on hypermedia-driven interaction among agents, so mostly on the agent dimension, but of course the interaction was through the environment because it was through the web. And in that work, we proposed a first set of design principles for REST-style web-based multi-agent systems with a focus on the Web of Things and the social web. Then we started to further abstract away those ideas, and that's when we started to discuss about Hypermedia MAS as a generalization of socio-technical networks. So here the objective is to reuse the design rationale behind the web architecture to design multi-agent systems that can inherit the architectural properties of the web. So here we talk about internet scalability, openness, long-lived systems. So now here the focus was not only on the agent dimension, but mostly on the environment dimension. So hypermedia-driven interaction between agents and their environment, where the environment dimension can also reify the other conceptual dimensions. And we can see that very well in Giacomo with the organization dimension. And then here we started to look at the new set of principles that are closer to architectural design choices and also go beyond REST towards asynchronous interactions. And some of our ongoing work as part of the HyperAgents project, this is a project between France and Switzerland with the group of Fabien Gandon and the group of Olivier Bossier. We are continuing forward to distill this idea. So one of the things that we are looking at is to define a clear-cut design rationale for Hypermedia MAS that would bring everything together. And now we are also more focused on the other 2 dimensions. So we are looking at declarative languages and hypermedia-based mechanisms for interaction in multi-agent systems, and the same for regulation in multi-agent systems. And regulation, that is one of the areas that are not so well explored in the web community, and where I think that multi-agent system research can bring a lot of insight. So what we've seen so far is that with the Sing description, for instance, we have declarative specifications of interactions with devices, for instance. But for instance, other things like data licensing informations, API rate limiting policies, terms of services, and so on, how we are allowed to use those devices, this is something that is not currently being addressed. Okay, so this is the central tack of the work so far on Hypermedia MAS. And then from a conceptual standpoint, where we started from was, in fact, the Giacomo Metamodel. So this is where we started from for socio-technical networks. And what we did is we started to abstract away from the different dimensions. So in a socio-technical network, an agent can also be a person. So it's not just an artificial agent, it can be a human. Then we also abstracted away the environment dimension. So we used initially a definition for artifact that was very broad. And from the organization dimension, we only kept 2 main concepts, which were role and groups. We were not so much addressing the organization dimension at that time. And essentially what we did with socio-technical networks was to define a hypermedia-based mechanism for uniform interaction between all these elements. And this is what we called hypermedia-driven socio-technical networks. Later, to move from socio-technical networks to further generalize towards Hypermedia MAS, what we did essentially is we further generalized the hypermedia-based mechanism to support uniform interaction, not only among agents, but also with entities across any existing or future conceptual dimensions in multi-agent systems. And this is essentially what we call Hypermedia MAS right now. And here we are focusing more at the moment on the environment dimension. Okay, so this was the big picture of the work we did so far on Hypermedia MAS. And I hope I also managed to give an overview, a shy overview of other work in the community. And now I will go a bit more into the details of what we did so far. So starting with socio-technical networks and then going towards Hypermedia MAS. And at the end, I will also bring up a concrete case study that looks at the industrial manufacturing system we developed at Siemens. So to begin with, socio-technical networks, we were defining these systems as dynamic networks of people and things that are interrelated in a meaningful manner via typed relations, friendship, ownership, provenance, collocation, and so on. The core idea was that we were modeling people and things that are actively trying to influence the environment as agents and things that passively augment the environment with new capabilities as artifacts. And then the typed relations would enable informed crawling, support reasoning, and can also be extended with any additional domain or application-specific relations. And agents, both human and software, can rewire the networks in pursuit of their goals. So that was that core idea about flexible autonomous use of hypermedia, which was already there in socio-technical networks. Why would that be interesting? Where our initial motivation for socio-technical networks actually started from a human-computer interaction perspective. So the idea was to allow people to interact in a uniform way with a vast, evolving, and heterogeneous Internet of Things. Then these arguments morphed more towards creating flexible mashups, composed of services provided by heterogeneous providers. So this was going more towards the architectural aspects and how can we integrate siloed systems. So again, bringing together autonomy and hypermedia-driven interaction. What Simon, one of my colleagues, would call systems that are ideally interoperable. Simon is one of my colleagues here in St. Gallen, and he was also part of the team at ETH Zurich that launched the Web of Things. And this is actually how we started to interact and to work together by bringing together autonomy and hypermedia-driven interaction. So really what we were trying to do with socio-technical networks was to break these silos. And I'm just going to show you a quick example of how this could be useful. And this is a demonstrator that we showed at the Web of Things workshop back in 2016. So in this scenario, the idea was that we have David right here, who has a distributed social graph across Facebook, Twitter. These are heterogeneous platforms. We saw earlier the heterogeneity problems we have with Twitter, the same problems we have with Facebook, and so on. And in this distributed social graph, David has a number of friends. And essentially what we were trying to do was to create a hypermedia overlay on top of this heterogeneous environment that would allow our agents to break the walled garden, so to navigate across the silos. And essentially, this is what we were showing in our demonstrator, that David owns a smart TV, and the smart TV is able to navigate David's distributed social graph to discover his friends and to discover also the TVs that are owned by those friends. And then it could start interacting with the other TVs to exchange recommendations and so on. And this is precisely the process that you see here. And of course, it's quite easy to navigate into a walled garden like Facebook and Twitter. The question then is, how do we navigate out? And the assumption that we were making here is that David's friends can also advertise their personal web ID on Facebook or Twitter and so on. So this is what allowed us to navigate outside of a walled garden. And then the TVs could discover one another, and then they could connect and start to interact with one another. So this was actually quite exciting to see at that time. So being able to deploy a hypermedia overlay on top of heterogeneous silos. And this was really showing that idea of having a hypermedia-based uniform interface for the social web and for the Web of Things. So this was before the standardization work at the W3C, so there wasn't yet a hypermedia-based uniform interface for the Web of Things. And of course, there were also challenges and limitations, in particular authentication of HTTP requests, but also API rate limiting. There is a lot of heterogeneity in that area of regulation. So to achieve this, what we needed was to have a narrow waist for this huge heterogeneous environment. And this is what we were aiming for with an ontological model for social technical networks. And this is a model that took a lot of input. So the Giacomo Metamodel, the environment as a first-class abstraction, various models for organizations and institutions in multi-agent systems, various ontologies from the web community, and so on. And what we got was the SDN ontology, which we were trying to use as a least common denominator for the social web and for the Web of Things. And in addition to this model, we also had models for defining hypermedia controls. So really, the focus here was on semantic interoperability and navigability. So to provide agents with this sort of hypermedia uniform interface. And I will not go more into the details. I will just mention that there were many open problems for which solutions were not yet available. So for instance, hypermedia APIs. Now there are many different ways to describe hypermedia APIs, Hydra, the scene description, and so on. And also another challenge that we had to solve was to integrate data from heterogeneous data sources through RDF, so RDF lifting and lowering. So now there are many advanced solutions for doing that as well. And without going more into the details, I will just show you quickly the sort of problems that we had to address and how this relates to the points around the web architecture. So the first point that we had to address was the uniform identification of resources. And of course, it's quite easy to say that, okay, we identify everything through a URI, but as soon as we go into the wild, well, out there, each API uses an implementation-specific identifier. So then how can we make that into a uniform, context-free identifier? Well, our solution was to embed the URI of the platform into the reference. So this is what you see here. So the Facebook identifier is essentially a string of numbers, and then we can embed the Facebook platform API to make this reference context-free. And the core point is that then dereferencing this API should also give us a specification that tells the client how to use this identifier. So this was all covered in there. So this was the problem of identification. Then in terms of formats, as we saw, JSON-based representation formats capture the syntax, but not the semantics. So to address this problem, we defined a simple mapping language that would allow us to extract RDF data from heterogeneous JSON representations. And lastly, to support hypermedia-driven interaction, there were multiple elements that we were using. So one of them was the social network metaphor, which allowed the discovery of agents, artifacts, agent description, which would allow to discover user accounts held by agents in various SDNs, hosting relationships, which would allow to discover affordances exposed by SDN platforms, and the hypermedia controls, which would give us really the means to enact affordances. So this would be an example of a hypermedia control defined with the SDN ontology. So this was pretty much where we started from. And of course, there were quite a few limitations with this prior work. So first of all, it was focused on the social network metaphor, the social web, and the Web of Things. Asynchronous interactions were not yet properly addressed at that point. So for instance, to observe an environment, an agent would have to constantly poll for updates by executing actions. And then at that time, semantic interoperability, the problem that we were looking at was mostly for REST style, REST-like RPC style, HTTP interfaces. So these were the silos that we were trying to bridge. But nowadays, we are way past those simple days with the Web of Things. So the Web of Things is already going outside of the web with new protocols such as MQTT and so on, which follow a completely different architectural style. So in this case, brokered PubSub. Okay, so do you have any questions so far on this work? Okay, so then I will continue to go forward with Hypermedia MAS. And I will soon get to the demos that I mentioned. So with Hypermedia MAS, what we started to do was to abstract away further those ideas. And one definition that we gave for a hypermedia multi-agent system is a system composed of people and artificial agents that are situated and interacting in a shared hypermedia environment that is distributed across the web. And the point here is that agents navigate and use the distributed hypermedia environment in pursuit of their goals, so pretty much how we use the web. And they can do that just by crawling the environment, or they can use a hypermedia search engine. And recently we developed a proof of concept for such a search engine for autonomous agents. And then, just by using hypermedia, so a single entry point and a set of semantic models, agents can discover various resources. So this could be devices, policies, specifications of interaction protocols, specification of organizations, but also affordances for interacting with such resources. So again, the core idea here is that agents use a hypermedia-based uniform interface to interact with the rest of the system. And ideally, just like we saw in the W3C Web of Things architecture, we would like our agents to be able to arrive and operate in any such environment. But the core point there, just like we saw with social technical networks, is that to achieve this sort of uniform interface, agents need to have a shared model of the world. So for artificial agents, this means that there is a model that is explicit either to the agent or to the agent designer that the agent is operating on. And we saw that the web's uniform interface is based on an evolving set of media types that capture various models. And in the same way, it's reasonable to assume that in a worldwide hypermedia MAS, we can expect a plurality of models as well. So it cannot be just one model. And this is what makes the problem even more interesting. And we can actually obtain such a uniform interface using any model or architecture for multi-agent systems. So I will show you briefly how we can obtain such a model with Giacomo and also with the FIPO abstract architecture. And essentially what we are aiming for with worldwide hypermedia MAS is to have this sort of linked hypermedia MAS that are different, but still they are interoperable to some extent. So in what follows, I will go very quickly through a set of design principles, and then I will show you two quick demos for Hypermedia MAS. So this is a set of principles that we proposed in a paper for the MAS workshop in 2018. You have the more detailed description there of the principles. Here I'm just aiming to give an overview of the design rationale, so just the gist of it. So the first design principle was about the uniform representation of the multi-agent system in the hypermedia environment. So again, here, the environment is a first-class abstraction. It's kind of hard to represent that in a single image, but you can, this image is actually trying to show a visualization of an RDF graph. So it's not just an RDF graph, but also the environment as a first-class abstraction. And the core idea behind this first principle is that agents can discover and interact with other entities simply by consuming and producing hypermedia, so in a uniform way. So to send a message, they would send a post request, they would use a put request to update a light bulb, and so on. Then the second principle that we defined is what we call the single entry point principle. And the core idea there is to maximize the usage of hypermedia in order to minimize the amount of knowledge we hardcode into the agents. So obviously, as soon as we hardcode something into the agents, this will increase tight coupling into the system. So to reduce that tight coupling, we want to put as much knowledge as possible in the hypermedia. So this would include the affordances, but also policies, specification of interaction protocols, specifications of organizations, and so on. And then the third principle is about observability. So this idea to allow agents to selectively observe parts of the hypermedia MAS that are relevant to their goals. So the idea here is to support scalability. So agents can handle larger hypermedia MAS if they can selectively observe part of the environment. And at the same time, the hypermedia infrastructure can serve more agents. And one of the models to which we apply these principles is the agents and artifacts metamodel. And I will go ahead and show you a demo of that. And the on architectural properties is not so much focused on functionality. So what we want to show here is that essentially we can achieve the same sort of design rationale that we have on the web. So what you will see in this demo is that in the first phase of the demo, I will have an agent running in a Giacomo application. The agent receives a single entry point, and from that entry point, it is able to discover the environment, which contains a robotic arm. Then in the second phase of the demo, we are going to add another node for the Hypomedia environment, and the agent is going to be able to perceive that new node being added. And then in the third phase, we are going to launch another Giacomo application with another agent that starts from a single entry point and creates a virtual artifact. In this environment, a counter, and starts to increment the counter. The first agent will be able to perceive that count, and once the count reaches 3, it will start to operate the robotic arm. So I will now switch to my browser. And you should now see a video stream from our lab where we have a robotic arm that we can access via HTTP. So this is the robotic arm that I'm going to use in my demo. And I will first need to register with the robotic arm, get an API key. Now, if I go back to the video stream, you will see that my robotic arm was activated. So I just need to get the API key here. Okay. So now I'm going to start the 2 nodes for the distributed Hypomedia environment. And what I'm going to do first is I'm going to register some resources on these 2 nodes. I will show you what happens in a bit. Now I'm going to start the first Giacomo application with the agent that discovers the Hypomedia environment. So what you can see in this output is that the agent started from a single entry point. And then from this entry point, it discovered the workspace. And in that workspace, it discovered the robotic arm that the agent is going to use. And if you go to my browser, this is what the agent actually sees. It sees a turtle representation of the environment that contains a workspace. Then the agent can navigate this environment. The workspace contains a Leobot robot. And if I dereference the URI of the robot, what I get back is a scene description with the affordances equals by this robot. My agent is able to discover the robotic arm. Now what I'm going to do is I'm going to create a link from the first node to the second node. If I go to my Giacomo application, I see now that the agent perceived this change in the Hypomedia environment, and it's aware that there is another workspace. How was the agent able to tell? Well, if I refresh this tab, you see that there was another link that was added to a workspace running on a different port, so on a different application. So this is how my agent was able to perceive that there was a change in the Hypomedia environment and there is a new workspace available. What I'm going to do next is I'm going to launch the second Giacomo application. And this is the agent that will create a counter, a virtual counter, and will start to increment the count. And what you see here is that the first agent is able to perceive the count. So the count reached 3, and now the agent is operating the robotic arm. So if you go back to the video stream, you see that it to move a block. And the way in which the agent is operating this robotic arm is based on HTTP requests that are being composed at runtime using the semantic affordances discovered in the Hypomedia environment. So essentially what we show here is that starting from a single entry point, just like we use the web, our agents are also able to discover the Hypermedia MAS and to interact with entities in the Hypermedia MAS. So do you have any questions so far about the demo? Okay. Jamie, yes.
Jaime has a question. Please, Jaime, if you want, you can open your audio or just write the question here.
No, unfortunately not, Jamie. We cannot hear you. Okay, so meanwhile, while Jamie and Arlison, I see, are typing questions, I'm going to go back because we are reaching the time limit. So I'm going to go back to my slides and to wrap up the presentation. So, okay, this was the first demo.
Jaime put the questions on the chat.
So the fact of registering the new resources is the way that the agents discover new elements. Yes, that is correct, Jamie. So the agents essentially here, they are able to perceive changes in the environment. So for instance, to make an analogy, just if I would have a tab and the page would get updated and I would get a notification, so like on Facebook and so on, then I would be able to see that change. Is it a broadcast? Everyone discovers everything. No, not exactly. So actually, there could be many different mechanisms here. So the protocol that we use is W3C Web Sub, which is a brokered publish subscribe protocol. So what this means is that agents have to subscribe to the sort of notifications that they would like to receive. So in our Giacomo application, actually, this is invisible to the agent developers and to the agents. So the agents would just focus on artifacts, and then they would receive the notifications from those artifacts. Yeah. Okay. So I also had here a tiny demo prepared for Jade. Yeah, so this is work in progress that we are doing right now. So given that the remaining time is kind of short, I will not go into this demo, but essentially the core idea was to show that we can create a hypermedia uniform interface for any model for multi-agent systems. And here, the FIP abstract architecture and Jade as the poster child implementation for the FIP abstract architecture is a very good example because the agent environment is not considered explicitly. But we can make it explicit when we design the hypermedia-based uniform interface. So going back to the idea of a uniform interface, which also goes back to the original idea for the web as an application integration architecture. So just like in the early days of the web, the idea was to create uniform hypermedia views of heterogeneous information systems. We can also create uniform hypermedia views of heterogeneous multi-agent systems. So to wrap this off, I will just mention briefly a demo that, a project that we did at Siemens, where we were trying to bring these concepts together for industrial manufacturing. And the domain problem that we were addressing there was that manufacturing lines are expensive to design and build, but they are also hard to reuse and reconfigure for even new generation of products. So a manufacturing line usually have a lifespan of 50 years, say, so tens of years, and it is tightly integrated and heavily optimized for a given type of product. And then a challenge here is how can we create batch size 1 products, so products that are highly customized, but at very low production cost. So at the same costs, ideally, for a batch of products. So the idea was really to repurpose manufacturing systems on the fly. And to make an intuitive analogy, what we were looking for was a middle ground between fully automated systems and what we currently have, which is production engineers manually configuring and programming the systems. So we were looking at ways to introduce knowledge into a system that would then be able to synthesize a production plan. And while so far I was mostly focused on the web aspects, in this project done at Siemens, we were mostly focused on how can multi-agent systems research contribute to practical applications at Siemens. And what we were using was the Giacomo platform for doing that. And we were trying to show all the benefits of the multi-agent oriented programming paradigm, which will be presented later in the week, I believe, by Jomi. So these were the various abstractions that we had there. So we had a Web of Things environment with devices, either using CoAP or HTTP. Devices would carry thing descriptions. Then on top of that, we bring our artifact abstractions. And then on top of that, at the very top, we have the multi-agent organizations, which would allow us to hot deploy manufacturing specifications on a running system. So this is one of the really nice features that we get with Giacomo. So multi-agent organizations are loosely coupled, so to say, to the agent dimensions through norms. So it really was a very interesting feature for Siemens in this context. And then to use artifacts, agents would either use plans available in their library of plans, or they would synthesize a plan based on semantic descriptions of artifacts, what we call here artifact manuals. So the concept of a manual is also part of the Giacomo platform, and the specific type of manuals that we were using were semantic descriptions of atomic operations. So we could then use classical planning to synthesize a production plan. And essentially, first an agent would try to select and execute a plan from the plan library. If no plan was available, it would synthesize a plan. If a plan is found, this is translated to agent speak and added to the plan library. And then the agent would try to achieve a goal. And this was another very interesting feature for at Siemens, that we could use automated planning to synthesize plans. These are usually not that easy to use in terms of programming, but then we can translate those plans to agent speak, and engineers can inspect and edit the inferred plans in a language that was designed for programming plans. So that was actually quite interesting to see, bringing those together. And the use case that we were looking at was the flexible assembly of customized furniture. There is a demo video that is available online, but you will have the link on the slides. But given that I'm reaching the time limit, I will just run to the conclusion slides with couple of statements to wrap up the discussion. So I hope I managed to convince you in this presentation that it is both timely and necessary to create thorough conceptual and technological bridges between these two communities, multi-agent systems and the web, and that the basic elements required to design and to deploy Hypermedia MAS are already available. So we are not yet to the point where we can build internet scale Hypermedia MAS, but we have the elements that allow us to move towards that direction. So thank you very much. Thank you very much for listening. And so I see a question from Jomi. In the case of planning, are scene description integrated? So very good question, Jomi. So in fact, if I go back to my slides here, so in fact, in this work, what we were using were semantic descriptions of Cartago artifacts. So essentially, we were using preconditions, postconditions, specifications of artifact operations. And then the artifacts would also come with a scene description. And essentially, the artifacts would then use the scene description to perform the actual requests for given affordance. So to answer the question, the planning was not directly using the scene descriptions, it was a layer above. So it was planning with semantic descriptions of Cartago artifacts, and then the Cartago artifact itself would use the scene description to enact an affordance or to activate an affordance. So feel free to speak, Jamie, for the question. I think it's much easier to interact.
Yes. Can you hear me?
Yes, now I can.
Okay. Excellent presentation, Andre. It's a pleasure to see you here. I'm a very fan of work you are conducting in the last years. My question refers to the term used that a uniform interface means having a standardized knowledge. And issue in knowledge representation for years. And I noticed that in all your demos, agents could interact, but it was a kind of line work, right? One does one thing, and then it passes the token to the another and continues, etc. In the case of if you need to have a cooperative action between several agents, how could you cope with this standardized knowledge, or the way that each agents represent internally this stuff? I'll try to explain the questions. One is when I'm navigating a web page alone and trying to do where are the good conferences to submit a paper and so on and so forth. Now suppose that me, Jomi, and Diana, we are together in the same room and seeing the same web page. Probably the navigation would be different, because people would exchange these decisions or knowledge they have. I know it's a difficult question, but I was wondering if this would be a further step in the work, or how to represent this in a kind of, how can I say, group knowledge or something like that, if you have some knowledge about ideas about that.
Yeah, so I think this is a great question, Jamie. I did not hear the full question because there were interruptions, but I think I got the main point. So the question is, if we need to achieve a uniform interface, and the uniform interface is based on standardized knowledge, how can we do that in a worldwide system, for instance? So could all agents agree on a single shared model? Well, would this be the question, Jamie?
Yes, yes. Yeah. I give you an example. We had a paper in IGCAI 2007 about interoperability of reputation. At the time, Laurent Vercouter was Etienne at the time. And agents were just sharing reputation values and reputation types. And this is difficult for just a single stuff. My question is, if they need to agree on domains or ontology of domains, I mean, there are some work in the W3C. I had a student in the past that worked with financial systems, and there is a thing called FIBO, which is an ontology for financial knowledge. The idea will have a shared ontology. I mean, you didn't mention in the talk how the agent part could assess a common ontology in order to help him to reason about these actions, the operational level. And what do you think of this problem in the research? It's complementary, some ideas?
Yeah, so this is a great question, Jamie, and I think this would be a great discussion to carry forward. So, so I have multiple answers to this question depending on how I approach it. So for sure, we cannot expect to have one single model for any given domain or any given application in a worldwide Hypermedia MAS. So just like the web's uniform interface is based on an evolving set of media types that capture different models. And for instance, if we talk about worldwide Hypermedia MAS, it is reasonable to expect a plurality of models. So this is also a problem that is very much studied in the semantic web community. So this goes towards ontology alignment. Some people are also looking at the cultural evolution of knowledge and so on. So this is not a trivial problem. So this is a very complex problem. But then the key point is that in this worldwide Hypermedia MAS view, we can also imagine linked Hypermedia MAS, where a Hypermedia MAS could be defined by an organizational boundary. And then the key point from a design perspective would be that as soon as an agent crosses such an organizational boundary, for instance, by enacting a role in an organization, in a Hypermedia MAS, it should be able to operate on a uniform interface that uses a model specific to that system. So it's a bit hard to answer very concisely, but just to make an analogy with the work we were doing on social technical networks. So essentially what we were doing there, we were trying to define a least common denominator for the social web and for the web of things. So this was a very abstract model that would allow agents to operate to some extent on any given social technical network. So they could use Facebook to some extent, they could use Twitter to some extent, but the Facebook model and the Twitter model are different. So this means that an agent that is more familiar with the Facebook model could exploit Facebook better, and an agent that is more familiar with the Twitter model could exploit Twitter better. Now, if you think about a Hypermedia MAS, two linked Hypermedia MAS, where one uses the Giacomo Metamodel, one uses the FIP abstract architecture. So to some extent, we can find some commonality between the FIP abstract architecture and the Giacomo Metamodel. So for instance, especially in the Jade implementation, we have this notion of container that contains other agents. To some extent, we can make a parallel between a container and the workspace in Giacomo. But of course, a workspace in Giacomo is something much more complex. It is a logical container maybe for agents, but also for artifacts. The concept of an artifact does not exist in the FIP abstract architecture. But still at a very high level of abstraction, an agent that has a model for the FIP abstract architecture could potentially be able to navigate a workspace in a Giacomo-based Hypermedia MAS to discover other agents in that workspace. Perhaps not artifacts, because the agent would not have a model of artifacts, but it would at least be able to navigate the system to discover the other agents. Then an agent operating on a Giacomo metamodel would be able to make use of both systems. So it would be able to use the Jade-based platform to discover workspaces, artifacts, and so on, agents, and so on. And it would also be able to make full extent of the Giacomo metamodel. So I will try to summarize the answer in a few words. So definitely this is a big problem. So it's a problem that, and for sure we can expect to have a plurality of models. So we cannot expect to have a single model. But the core point is that to achieve this sort of uniform interface within some bounded context, the agents that are in that bounded context have to agree on a shared model. How the agents agree on the shared model, I would see that as a complementary problem. Did this answer the question, Jamie?
Perfectly. I fully agree with you. I think that we'll never have a shared common model that, and I think that our inspiration is people. For instance, if chair to me and it's something to you, meaning have places for the arms or not, when I'm interacting with you, I can dynamically make this translation as far as you explain this to me. And this is some work that I have made in the past with some students again, regarding reputation. And some years later, we, Olivier and me, we have done some work in organizational models, meaning if you have a Moise agent, how we could, if he has the knowledge to do something, how could he interact with an agent that use another organizational model, for instance, like the one from Faber's. And I think that this kind of approach where you can use ontology as a bridge for translating concepts from one model to another, a simple one, as you mentioned, maybe I don't know what's an artifact, but I know what is simple. If it's something simpler, I will use the simple properties to interact with you. Thanks for the enlightening talk.
Thank you for your kind words, Jamie.
Thanks, Andre, for this very inspiring talk. Thanks for all these questions we have so far, for these discussions. I think we have time for one more question if someone wants to ask for. Andre, please.
So I saw that Jomi was typing a question.
Yeah.
Maybe, Andre, a very simple question. What is your opinion about some question that I am asked quite a lot? That the web is usually seen as a client-server model, as I guess in the REST approach, it's like that. On the other side, we have agents that are proactive and they have initiatives to interact with as an user, for instance. And you mentioned in your talk some progress in that direction about async communication.
Yeah.
Could you comment more on that? How to handle that issue?
Yeah.
I guess I know your answer, but I used to have this question quite a lot, and it could be nice to see your opinion. Thank you very much, and also thank you very much for your talk. It was a very, very nice talk. Congratulations for that, sharing your ideas with us.
So thanks very much, Jomi, for your kind words. And this is a great question. So it's a question that always pops up, especially in between the two communities. This idea of client-server interactions. So if we go to the web community, some researchers in the web community argue for applying REST ad literam. So if we have client-server, then we have to use client-server interaction. For instance, we cannot use asynchronous interactions in any way, because this would violate the REST architectural style. I disagree with that view, and Roy Fielding also disagrees with that view. I had a very nice slide on that, but already there was too much content for today, so I took it out. But really, REST was defined to meet the needs of the web of documents in the 90s. So REST was not defined for asynchronous interaction. So that is a limitation of REST, and Roy Fielding himself had to address that limitation in other work. Now, if we go to the MAS community, there indeed the criticism is that client-server is very constraining on the autonomy of agents. So there, everyone is very much fond of asynchronous interactions. So to answer the question, Jomi, what we do in our work is we take a middle ground approach. So for me, the key insight behind the client-server constraint is not the idea of having clients and servers. The key insight is a clear separation of responsibilities. A clear separation of responsibilities between the client concerns, which in the context of the web of documents are about presenting information to the end user, and the server concerns, which in the context of the web of documents are about storing data. So there is a clear separation of concerns there. And in the context of the web of documents, that separation of concerns is important because it allows the components to evolve independently from one another. So clients can evolve independently, doing their own business. Servers can evolve independently. In our work, we have a similar separation of concerns that comes from the separation of responsibilities between agents and the environment as a first-class abstraction. So it's not exactly client-server, but it uses an underlying principle, which is separation of concerns. And this separation of concerns allows agents and the environment to evolve independently from one another. So this is the sort of middle ground that we take in our work that we did so far. So we do not impose client-server separation of concerns, and we don't need to, because we have a different separation of concerns that achieves the same design goal at the system level, so allows agents and the environment, which in our case is hosted on web servers, to evolve independently from one another. And then how agents observe the environment, that's a different story. So some people in the web community will argue that they have to do polling. To me, that is not really, so it could be very useful for some use cases, but not for all use cases. And polling is not always the most efficient solution. So we could also have asynchronous interactions that go beyond the rest as it was classically defined. So did this answer the question, Jomi?
Sure. Thank you very much.
Okay.
Okay, thank you, Andre, again for this inspiring talk. I'm sure our community is very inspired and will possibly continue these discussions in the future. We have now to move on our conference. Again, Wesaac is very grateful for your presence here. And okay, we are finishing this first lecture, and I go to Carlos Pantoja to continue our session. Pantoja, contigo.
Once more, thank you, Andre, for your talking. Then now we're gonna proceed to our technical session. So let's go back to Portuguese. Então, pessoal, vamos já proceder já direto para a nossa sessão técnica. Como a gente vai fazer? Eu vou fazer o broadcast dos vídeos aqui para vocês, para quem não conseguiu baixar os vídeos, quem não conseguiu assistir os vídeos, eu vou deixar passando aqui todas as apresentações, e após as apresentações, as perguntas podem ser feitas. Se vocês quiserem fazerem por aqui ou pelo Slack, fiquem à vontade. A gente está com a equipe acompanhando pelo Slack, a gente está com a equipe acompanhando por aqui também. Então, a gente vai fazer o broadcast, vai dar 5 minutos para a discussão das questões. Se vocês já tiverem visto, já tiverem outras pessoas, eu peço para que